Hello and welcome to the Chemistry Made Simple podcast. I'm your host, Matthew Macario, and this is the podcast where you get chemistry confident and we take you from point A to grade A. Hello, welcome back to the podcast. I hope you're well. In this episode, we're going to be talking about how to determine the rate equation. So over the last few episodes, we've talked about rate of a chemical reaction and that we can write an expression relating the rate of reaction to the concentration and something called the rate constant. And in this episode, we're going to talk more about how to determine what the rate equation is, what the rate constant is for a particular reaction. So if you haven't listened to the last two episodes, I would suggest going back and listening to those before continuing with this. Okay, so you'll recall that we previously mentioned that there is a rate expression that says that the rate of reaction for a reaction that is reactant A plus reactant B gives products C and D, let's say. So our rate equation would be rate equals the rate constant K times the concentration of reactant A times the concentration of reactant B. But we may have indices associated with the concentration of A or B. We may, for example, square the concentration of one of those because its effect on the rate is not linear. So how do we determine what those are? Well, the way to do this is by running a series of experiments of the same reaction at the same temperature and measuring the rate in each case. So through this series of experiments, we'd start with the concentration of A and the concentration of B slightly different from the next experiment. We would alter the concentration of one reactant at a time. So in the first and second experiments, we would perhaps keep the concentrations of reactant A the same and change the concentration of reactant B. And then by measuring the rate of reaction in both of those experiments, we can see whether the change in concentration of reactant B is directly proportional to its concentration or is proportional to the squared concentration of reactant B, or is it potentially not affected by reactant B. That can happen too. And also we would do a couple of experiments where we're changing the concentration of reactant A and not reactant B so that we can see the same effect for reactant A. Remember, we're keeping the temperature the same in each of those occasions so that our rate is not affected by a change in the rate constant and the temperature. You'll get a table of data from that series of experiments, and actually it's very common to be given that table of data without having to do the experiment. If you're doing an assignment, if you're doing an exam question, you'll very often be given that table of data and be expected to work with it. So at that point, you should be able to have worked out that the rate is equal to rate constant K, and you'll know what the indices associated with reactant A and reactant B are. So the next thing we need to do, and we can do this from the same set of data, is we can work out what the rate constant K is at the temperature that the experiments were conducted at. We have the rate of reaction. We were given that in the table of data. We know that rate equals K times, for example, concentration of A squared times concentration of B. So now we can just use a little bit of algebra to calculate what the rate constant is. And you can check this by putting it into more than one of the experiments in that series of experiments just to check that actually the figure that you're coming up with does tally, does work, it's consistent, you've calculated it correctly. Great, so now you know that the rate constant equals K, and you know what the value of K is, times concentration of A squared times concentration of B in this case. And therefore you know that the order of reaction relative to reactant A is 2 because we squared the concentration of A, and the order of reaction relative to reactant B is 1 because we didn't raise the concentration to any power. And we can see from that also that the overall order of reaction is 3 because we can actually add together the order for A and B, and that's 2 plus 1 obviously is 3. Okay, let's talk briefly about another way of working out the order of reaction for a particular reactant. We can run experiments where we keep the concentration of one reactant the same each time and change the concentration of another reactant. Let's say we're changing the concentration of reactant A. And then we can measure the rate of reaction in each of those experiments at the same temperature again, of course. Then we plot a graph showing the concentration of the reactant we were varying the concentration of on the x-axis and the rate of reaction on the y-axis. We can look at the shape of that graph and determine the order. So for a reaction where the reactant is first order, we'd see a linear rise in that graph. Where the concentration is 0 and the rate will be 0, at higher concentrations, the rate will be higher. So it's a linear relationship for a reactant whose order of reaction is 1. But in a different reaction, we might find we vary the concentration of a reactant, plot the rate, and we find that the rate does not change. It's consistent throughout a range of concentrations of one of our reactants. And that will be a reactant at 0 order. Its concentration won't appear in the rate equation, even though it is part of the chemical equation, because its concentration does not affect the rate. How about for a reaction where we plot the varying concentration of a reactant against the rate, and we find that we have a curve where the concentration is 0, the rate is 0, but as we increase the concentration of our reactant, the rate increases exponentially. It's an upward curve rather than a straight line. That occurs where the order of reaction for that reactant is greater than 1. Okay, so we've talked about running experiments where we keep the temperature the same because we wanted to keep the value of K the same so that we could determine the actual rate equation. Once we're happy with the rate equation, we might want to know what is the effect of changing the temperature on the rate constant. So we can run a series of the same experiment, the same reaction, where the concentrations are the same at the beginning, but we run the experiment at different temperatures and obviously measure the reaction rates. And because we know the rate expression, we know whether the reactant A and reactant B are 0 first or second order, for example. We can calculate K in each of those cases. So we can therefore see what the effect of changing the temperature is on our rate constant K for that reaction. Okay, so let's just have a quick recap of what we've talked about today. We've talked about how we can work out the order of reaction for the various reactants within a reaction. We can do that by using data from experiments. We can use the graphical method as well of looking at the shape of the graph for a particular reactant for concentration versus the rate. We can work out the value of the rate constant K as well. Once we know our rate expression and we have data for the concentrations and for the rate of reaction, we can use a bit of algebra to work out what the value of the rate constant K is. And then we've talked about how we can work out the effect of temperature on the rate constant K by running different experiments at different temperatures. So that brings us to the end of this episode and this topic. Hope that's been really helpful. If you have any quick questions, please do contact me. If you have any deeper questions, also contact me and I'll tell you how you can work with me as well. The best way to get in touch with me is on Instagram at Chemistry Made Simple. You can also email me, matthew@chemistrymadesimple.net if you'd like to as well. Until next time, do look after yourself and goodbye. Thank you for listening to this episode. I hope you found it useful, and if you have had value from it, do consider visiting our Patreon community at patreon.com/chemistrymadesimple, where you'll be able to ask deeper questions about this topic and get more support for your studies too. So I look forward to speaking to you again in the next episode, and until then, do look after yourself and goodbye.